Hi Wayne, hi Travis. This is John Whitaker for the Probability Graduate Level class. And this is our 22nd video lecture. And today we're going to concentrate on computing probabilities of events by conditionally. And so we're going to start off today with looking at a definition. So our definition is about an event. So let E sub 1 be an event, and we're going to define a random variable called the indicator function. Then the indicator function, I shouldn't say function, but indicator random variable, is denoted by x sub pi and given by x sub ei is equal to 1 if, this shouldn't be ei, it should be e1. If e1 occurs, and 0 if, or otherwise. Okay. So here's a fact. Turns out that the expected value of this indicator function is the probability of the event E1 occurring. We'll prove that. I want you to notice, before we move on here, I want you to notice that the indicator function, again, here just to say state, this should be E1, I don't know why I wrote that. The indicator function is a discrete random variable. Okay? So here's the proof. Okay, note the expected value of the indicator function of E sub 1 is equal to the sum over all output values of E sub 1 times the PMF of x of E sub 1. But here, the output values are 0 or 1. And so, very quickly, this is 0 times f of 0 plus 1 times f of 1. But what is f of 1? That's the probability that x of E sub 1 equals to 1. But when does x of E sub 1 equal to 1? It equals to 1 when E sub 1 occurs. So that's the same thing as the chance that E sub 1 happened. And so that's when we get the result. Okay. As another fact, the conditional expectation of x of E sub 1 given some random variable y equal to y, that's equal to what we'll say is the probability, conditional probability that E sub 1 of E sub 1 given y is equal to y. Now look, this is a random variable with respect to y, some function of y, and so is this, okay? Now this fact is true regardless of whether y is a discrete or continuous random variable. But the case where y is continuous has a proof that is beyond this course. So we'll only look at the case where y is discrete. So prove when, assume y is a discrete number. Okay. Okay. So the expected value of x of e sub I, e sub 1, given y equal to y. Well, that's equal to the sum over all x's, x of e sub 1 again. Well, that runs from 0 to 1 of x sub e sub 1 times the joint PMF okay. So that's equal to, well, of course, when x of e sub 1 is 0, we get 0. So this is just equal to f sub x of e sub 1 given y. Here, this will be 1, x of e sub 1. Well, this is 1. Y given 1. And what that is, just don't forget, that's the probability that x of e sub 1 equals to 1, okay, and y equals to y over the probability that y equals to 1. But that's nothing more in terms of events of the probability that x of e sub 1 equals to 1 given y equals to y. But x of e sub 1 equaling 1 is the same event as e sub 1 occurring. So that's the same thing as the probability of e sub 1 given, this should be little y. And that's big Y. That's what I'll write. And that concludes the theorem for the discrete case, and that's the only case we're looking at. Next, we want to have a fact in 2 parts. It says the following. It says the probability, this is part A. It says the probability of some event e sub 1 is equal to the sum over all y values of the probability of e sub 1 given y equal to little y times f sub y little y, in this case PMF, if y is a discrete random variable. B, the probability of e sub 1 will be equal to the interval from from minus infinity to infinity of the probability that E sub 1 occurs given y equals to y times f sub y to y d1 if y is a discrete. Okay, so let's prove both of these. First of all, notice that the probability of E sub 1 is equal to the expected value of x sub E sub 1. And by a previous fact that we had about conditional expectations, this is the expected value of the expected value of x sub E sub 1 given some random variable y. We just had a fact about that. That's the expected value, but the conditional expected value is the fact that I'm referring to, of the probability of E sub 1 given y equals y. And we think of this as a random variable, some function of y. Now, so for part A, if we'll suppose y is a discrete random, then the expected value, the probability of E sub 1, which we've already worked with and shown that it's equal to the expected value of the probability of E sub 1 given y equal to y. Okay, so this is a random variable here that's a function of y, and y is discrete, so y running from whatever it does of this random variable output values times f sub y to y. And that's what we wanted to show in this case. Part B, suppose y is a continuous random variable. Then the probability of E sub 1 is equal to, as we said before, is the expected value of the probability of E sub 1 given y equal to y. What that's equal to when you're in a continuous case, okay, this is nothing more than the integral from minus infinity to infinity of this function of the random variable y, probability of E sub 1 given y equal to y, times its p df, f sub y, dy, and that's what we want to prove. So we have the result in both cases. The remaining part of this lecture will be looking at three examples, the first of which is kind of short and abstract. Okay, so as an example, suppose that x and y are independent continuous random variables having density functions f sub x and f sub y of y respectively. Someone could say, find the probability of this event, that x is less than y. Now, these are continuous, and we can figure this out by looking at through calculus means, where we would draw a region that we're integrating over, and we come up with the right answer. But here's the way I'm going to look at it, based on our current point of view or current emphasis. The probability that x is less than y is really equal to, okay, so these are continuous random variables, is the probability of x being less than y, given, that's that event, y is equal to little y, and we're going to integrate this from minus infinity to infinity, and then I would have f sub y of y dy here, and this is by the previous fact. Okay. Now, the next thing is that we're given that y is equal to y, a little y, so I'm going to say this is the same thing as the integral from minus infinity to infinity of the probability that x is less than the little y, given y is equal to little y, f sub y of y dy. Now, because we're talking about continuous random variables, well, let me back up. First of all, we know that x and y are independent from each other, and so here, this is the same thing as random variables. This is the same thing, minus infinity to infinity. The probability that x is less than y, that's what this becomes, times f sub y of little y dy. Now, because x is continuous, being less than y is the same thing as being less than or equal to y. This is equal to the interval from minus infinity to infinity of the probability that x is less than or equal to y times f sub y of y. Now, the probability that x is less than or equal to y, this should have dy with it, that can be represented, minus infinity to infinity, by its CDF. So f sub x evaluated y, f sub y of y dy, where f sub x of y is equal to the integral from minus infinity to y. So it's the CDF, the cumulative distribution function of x. So it's minus infinity to y is the integral limits of f sub x of x dx. Okay? And so that's the way that I will leave the answer. That the probability that x is less than or equal to y is this, where you could put this in its place. And that is what we get when we're using calculus and looking at regions of integration. Okay. We will conclude with two examples that involve conditioning. And they're lengthier examples. Okay. An insurance company supposes that the number of accidents that each of its policyholders will have in a year is Poisson distributed remember what that is. Poisson is a discrete random variable, and it's f of x is equal to, P of f, e to the minus lambda, lambda to the x over x factorial. And x runs from 0 to infinity. With the mean of the Poisson depending on the policyholder. Okay. So the number of assets they have in a given year is given by this function for each individual person. The lambda, though, that's involved here depends on the person. Okay? That's what this says. And here's what it says. If the Poisson mean so the mean could be anything, okay? Of a randomly chosen policyholder has gamma distribution. So what could the lambda be? Well, it isn't the same. It has lambda distribution. I'm sorry, it has gamma distribution. Gamma is a continuous random variable now. With density function g of lambda, so it is a density function for the random variable, for the variable lambda. It's equal to lambda e to the minus lambda, where of course lambda has to be greater than 0. And so here, let's stop for a second to recall the density function of a gamma distribution, of a gamma random variable. A is, so here we can write it, if you will, as gamma of x. And it was lambda times e to the minus lambda x. This was in the definition here of what it meant to be gamma. Lambda of x raised to the alpha minus 1 over the function gamma of alpha. So that's what it was. All right. So this is kind of a parenthetical expression. So comparing that, and let's call this f of x, so that I don't need to use g of x. So in g of lambda equal to lambda times e to the minus lambda. So I'm looking here. here, in comparison, lambda is lambda, this lambda is playing the role of x, okay? And so, this is lambda here. What has got to be in front of the x? Well, this is just lambda. What's in front of x has got to be 1. Here are lambda or gamma. We have parameters. I should say this. Has parameters. Is a distribution. Gamma distribution. Yes. With parameters, okay, so the lambda here is 1 for this guy. Okay? And here, this is 1. This x is being played by lambda. And that's this part right here. What's it being raised to? It's being raised to the 1. That means that alpha must have been equal to 2. Okay. The question is, what is the probability that a randomly selected policyholder, okay, has exactly n accidents in the given year? This year. We're going to set up some random variables here. And use the fact that we just proved to get the solution. So we're going to let x equal to the amount or the number of accidents the chosen policyholder has in the year. Okay? And we're going to condition this, that involves conditioning, based on y. We're going to say, let y, okay, be the Poisson mean number of accidents per year for this policyholder. So conditioning on y, we have. So remember from that previous fact, the probability of e sub 1, so I'm going to put this in parentheses, what I'm using, is equal to, well, we have a gamma distributed random variable. So this is going to be minus infinity to infinity. Okay. Well, in general, this is what it is. And it's probability of e sub 1 given y equals y times f sub y of y. That's dy. That's what I'm using. So what do we have in our situation? Well, really what we're going to be, the e sub 1 is that x, the number of accidents for that particular chosen person, is equal to n. So that's what we're going to be working with. So, here's what we have. The probability of x is equal to n, so we're interested in, is equal to, here, because the PDF f sub y is only defined for y values bigger than or equal to 0. We have from 0 to infinity, defined to be non-zero. Of the probability of x equals to n given y equals to little y, no, y equals to lambda, times, here we denote this, it's P, the PDF of y, we denote it by G of lambda, D lambda, okay, that's what we're having, and that's equal to, well, I'll have one intermediate for the step. The probability of x is equal to n, given y equal to lambda. Here, this was defined to be, I think, lambda times e to the minus lambda, d lambda, that's what g lambda was. Now, if you're given y is this specific lambda, remember this is the integral from 0 to infinity, what you end up getting is an integral from 0 to infinity. Here, so we know that the lambda involved, or that the mean involved for the Poisson random variable for this particular policyholder is lambda. So given that, this is where we have the advantage of conditional probability being easy that we put ourselves in that position. The probability that x is equal to n given that is, so it would be e to the minus lambda, lambda to the x, but x is n, over n factorial. Here I have lambda, e to the minus lambda, d lambda. This is equal to, I can pull out the n, because I'm integrating with respect to lambda, so I pull out the n factorial. Here it would be the integral from 0 to infinity of e to the minus 2 lambda, and then this would be lambda to the n plus 1, d lambda. So I've got to somehow figure out what this integral is. Okay, so I'm going to stop there. So the way we're going to figure out what this integral is we will consider a gamma distributed random variable. So this kind of looks like a gamma distributed random variable. I'm going to call it capital lambda. Okay, capital lambda. With parameters. Okay, so forgive me. The alpha is going to be equal to n. Remember, this usually the alpha that's involved here is right here. What we have is a power for a gamma. Is usually alpha minus 1. So here, this needs to be n plus 2, so that when I subtract one from it, I get that power. And lambda equal to, it looks like 2 here, where this is the variable, integration, and this is the number up front, which is normally the lambda. Okay, so that's going to match that integral, but this is what we're thinking about for a second. And that is equal to, okay, I'm sorry. Then 1 is equal to the interval from 0 to infinity of F sub lambda of x. I'll call it lambda, d lambda, which is equal to the interval from 0 to infinity. Well, I should say minus infinity. Okay, this is the PDF. Okay, what is this? The PDF is a lot of times 0 where it's non-zero is when the lambda is bigger than or equal to 0, so we integrate from 0 to infinity. Here it would be lambda was involved with our parameter was 2 e to the minus 2 times the variable, which is lambda here. Then it was lambda to the lambda times x. X is lambda. The lambda involved is 2, so it's 2 lambda raised to the alpha minus 1, that's n plus 2 minus 1, so that's n plus 1, all over gamma of alpha, and here gamma of alpha is equal to gamma of n plus 2, I think, and it's d lambdas. That's what we'd be looking at. The gamma of n plus 2, remember, we proved that in the last homework assignment, a formula for that. That's just n minus, or n plus 1 less than what we're taking gamma of, factorial. So this is 1 over n plus 1 factorial. Here, this is the interval from 0 to infinity. And let's see here. I can notice that I have 2 here and a 2 to the n plus 1 there. That makes 2 to the n plus 2 that can be pulled out. So let's just put that in top. Okay, and what's left is e to the minus 2 lambda. Then this will be lambda to the n plus 1 d lambda. Well, that's the interval we want. So that tells me the interval from 0 to infinity of e to the minus 2 lambda, lambda to the n plus 1, d lambda, has got to be equal to 1 divided by this, which equals to n plus 1 factorial over 2 to the n plus 2. So, the probability that x is equal to n, which we have currently as 1, so I'm looking over here, it was 1 over n factorial times the interval from 0 to infinity of e to the minus 2 lambda, and it was lambda to the n plus 1, d lambda. So using the trick and the observation that we noticed involving a gamma distributed random variable, we know what that interval is. Okay? So this would be equal to 1 over n factorial. Here's n plus 1 factorial over 2 to the n plus 2. So that yields n plus 1 over 2 to the n plus 2. And that's the answer for this problem. One last example. example is suppose that the number of people who visit a yoga studio, also called an academy, each day is a Poisson random variable with mean lambda. Okay. Suppose further that each person who visits is independently female with probability P, and male with probability 1 minus P. This is like flipping a coin. So a person comes in, that's like a coin flip. Okay, they're either heads or tails. Okay, female or male. And then another person comes in, and that's like another coin flip. They're either female or male. Okay. Okay. So those are independent from each other. Each person that walks in, their sex is independent from the previous person's sex or anybody else that walks in. So here is find the joint probability that exactly N women and M men visit the academy today. So here's the solution. So we're going to find some random variables. We're going to let n sub 1 equal to the number of women who visit the academy. We're going to let n sub 2 equal to the number of men that visit the academy. And then we're going to let n be n sub 1 plus n sub 2, which is the total number of people who visit the Academy today. And what we're looking to find is the joint PMF, okay? We're looking to find the probability that n sub 1 equals to n and n sub 2 equals to m. That's what we're looking for. So we're going to condition that event based on big N. And use our formula, the last thing that we've proven during this lecture. And remember, big N is a discrete random variable in this case. That's good. Last time it was continuous in our last example, gamma. Okay. So here's what I want to tell you. Note, the probability that n sub 1 equals to n and n sub 2 equals to m. That's going to be a sum over all values. I'm going to call I. The probability that n sub 1 equals to n, n sub 2 equals to m, given n equals to I, and then I need f sub n of I. Okay, that's by our formula what we have. So the way that I'm going to rewrite that is this is the sum, it's I going from 0 to infinity, of the probability that n sub 1 equals to little n sub 2 equals to m, given n equals to I, and the this part right here, the f sub n I, is nothing more than the probability that n equals to I. Make that substitution. Now, for that part, what we're thinking is n can be anything, m can be anything, just in writing down what we have with this sum. And but they can be anything, but we're going to think of them as fixed arbitrary things. And I is changing. It's running from 0 to infinity. But here's what I want you to notice. As I changes, the only way that we can get something here that's non-zero is when the I is equal to n plus m. So here, note the probability that n sub 1 equals to n and n sub 2 equals to m, given n sub big N equals to I. This is equal to 0 all the time when I is different than n plus m. So in our sum, where we're trying to compute the probability that n sub 1 equals to n and n sub 2 equals to m, that's really just one item. It's the probability that n sub 1 equals to n sub 2 equals to m, given n equals to, here it's n plus m, times the probability that n equals to little n plus m. Now that's equal to this conditional probability given big N is equal to n plus m. And remember, n was Poisson distributed with lambda, with the parameter lambda. So this is e to the minus lambda, lambda to the n plus m, all over n plus m factorial. That's that PMF evaluated at n plus m. So what we've got to work on is this conditional probability. Now, the probability that n sub 1 equals to n sub 2 equals to m, given n equals to n plus m, where each person is independently a female with probability p, can be thought of. So this conditional probability can be thought of as a binomial random variable with n plus m number of trials and the probability for success, we'll think of that being a female, equals to little p. So, what we're looking for, the probability that n sub 1 equals to n sub 2 equals to m, okay? That's equal to this guy right here, times this e to the minus lambda to the m plus n over m plus n factorial. And now I'm going to substitute in the PMF for a binomial with those parameters. So that's equal to, so here it will be n plus m, n plus m choose n, okay? Then it would be p to the n, 1 minus p to the m, n minus, no, just m, okay? Then it would be e to the minus lambda, lambda to the m plus n, over m plus n factorial. And I'm going to rewrite this in a certain way. So here, this is equal to, well, this is n plus m factorial over, this will be m factorial, n factorial. Here I have a 1 over m plus n factorial. Here I'll break up this lambda to the m plus n as lambda to the n, and then combine it with this, so p times lambda to the n. And then we have 1 minus p, and then the lambda to the n, times lambda, raised to the m, and then we can write this down as e to the minus lambda. I'll do one more. So this n and plus m and m plus n, they cancel with each other, and so we're left with 1 over m factorial, n factorial. p times lambda to the n. This is 1 minus p times lambda to the m. Here, you can rewrite this e to the minus lambda. It's e to the minus lambda p times e to the minus lambda times 1 minus p. And I'm going to reorganize things for a second, then make some observations. This 1 over m factorial, let's make it m factorial. P to the lambda to the n times e to the minus lambda p, and then we're also going to have 1 over m factorial. This is going to be 1 minus p times lambda to the m, and then here's e to the minus lambda times 1 minus p. Okay, that's the answer. That's a way of leaving the answer. But I want to do one little observation, okay, about this. So some observations. Okay. Note the probability that n sub 1 equals to n. Well, that's equal to the sum as m runs from 0 to infinity of the probability that n sub 1 equals to n, and, so that's the joint PML that's going right, n sub 2 is equal to n. Now, that's equal to the sum over all m values. We just found this. Okay, so it was 1 over n factorial, probability p times lambda to the n, e to the minus lambda p times 1 over m factorial times 1 minus p times lambda to the m, e to the minus lambda times 1 minus p. I can take out everything that has n in it and rewrite this, if you will, most of the things that just have n in it. 1 over n factorial and beyond. P to the lambda to the n, and I'll take out this e to the minus lambda p. Here I have a sum as m runs from 0 to infinity of 1 over n factorial. 1 minus p times lambda raised to the n, e to the minus lambda times 1 minus p. Okay. Now, this is a mistake on my part. So this shouldn't have been n, this should have been m. This should have been m. And what we recognize here is this is a PMF. Okay. It's a PMF of a Poisson random variable. Poisson random variable with parameters So the lambda here is, so let's see. So what was e to the minus lambda, lambda to the x over x factorial. And we'd be summing up over the x's, okay? So here, it's parameters lambda times 1 minus p. Oh my goodness, I did all that work and never turned the camera. Okay, I'm sorry. I know we're going over, but this was my observations. I was looking at the probability that incident one each. I'm very sorry. I was looking at this, and so what I said was, to find this probability, what you do is you sum over the joint. And this is nothing more than the PMF of n sub 1. So we sum over the joint. We found that. We sum over the other variable values for the joint. And I know what that is. And so I wrote that down from my previous work. And then I could pull out certain parts beyond the sum, outside the sum, because they did not depend on the index variable. And then when I looked right here, I said, this part right here reminds us of a PMF of a Poisson random variable, that's what I'm saying, with parameters lambda times 1 minus p. So e to the something raised to the index over the index factorial. It's perfect. Sorry about that. Yeah. And so, to finish it up, excuse me. To finish that up, okay. That, of course, is 1, the sum. So we get 1 over n factorial p to the lambda to the n, e to the minus lambda p. Now we would get the same thing. So go ahead and make this up. So n sub 1 is a Poisson random variable. With parameter, it's a lambda p. Okay? Similarly, n sub 2 is Poisson. You did the same type of work. N sub 2 is Poisson with parameter lambda times 1 minus p. Thus, what we found is that n1 and n2 are independent. Random variables. Okay. And that's what we'll conclude with. Thank you very much for your time.